Over the past 4 decades, cosmologists collected vast amounts of data on the anisotropies of the relic radiation from the Big Bang, the cosmic microwave background, which indicate that the early universe indeed started simple. Statistically, the initial conditions can be summarized on a single sheet of paper. After Albert Einstein derived in November 1915 the equations describing the gravitational evolution of the universe, it was realized that the simplest solution to these equations is for a homogeneous and isotropic distribution of matter and radiation. Homogeneity means that the densities of matter and radiation are the same everywhere. Isotropy means that the universe appears to have the same properties in all directions. This simple cosmological solution of Einstein's equations was derived by the Soviet mathematician Alexander Friedmann a century ago in 1922. This solution is currently recognized as the Friedmann-Lemaître-Robertson-Walker (FLRW) cosmological model. The reason this simple model is celebrated today is because it describes the data on the expanding universe to exquisite precision. On large scales, the universe appears to follow the simple FLRW model, while on small scales, inhomogeneities grow by their self-gravity and collapse to make galaxies and clusters of galaxies. The formation of structures out of the primordial inhomogeneities imprinted on the microwave background is not isotropic. The collapse first proceeds along one axis, making a sheet, then a second axis, making a filament, and finally along the third axis, making an object like our Milky Way galaxy. The success of the FLRW model means that cosmic time is well defined, and clocks can be synchronized to a high precision throughout the observable universe. In fact, time is ticking at the same rate everywhere to within 1 part in 100,000. This is why we can learn about our own history by studying galaxies far away with the Webb telescope. What we see at great distances is how the infant universe looked like when light from these ancient galaxies was emitted long ago. Given that the cosmos evolved statistically in the same way everywhere, this educates us about our own history. By peering deep into space, we observe the cosmic roots of the Milky Way, inside of which the Sun formed, leaving behind debris that made the Earth, on which life as we know it evolved. Cosmology resembles a spherical archaeological dig from the inside out, for which the outermost layers are the most ancient. By studying light that was emitted early on from far away, we can recreate the scientific version of the story of Genesis. This resulting homogeneous and isotropic FLRW model is consistent with all observational data on the horizon scale of the universe to within 1 part in 100,000. What would constitute an isotropic but inhomogeneous universe? The answer is spherically symmetric onion shells of variable density centered on us. This requires us to be at the center, violating the Copernican principle, which posits that we do not occupy a privileged location. What would constitute a homogeneous but not isotropic universe? The answer involves a uniform distribution of matter or radiation in a space-time that expands at different rates in different directions. This introduces preferred directions into our cosmic landscape. Did our universe start isotropic? The answer is unclear. If we were able to detect gravitational waves on tiny centimeter wavelength scales, generated less than a quectosecond after the Big Bang, then their anisotropy on the sky could have informed us about the level of anisotropy that existed at the beginning, around the Big Bang. But for now, we can only detect space-time fluctuations on much larger scales that entered the horizon of the universe when it closely resembled the FLRW model. Hence, we cannot say much about whether the infant universe resembled a needle or a sphere. Thank you so much for watching. See you again in the next video. Until then, as always, keep looking up, stay curious, and dream big.